Hello grade 11s and welcome to another example involving Coulomb's law. This example says a small positively charged pith ball A is held at rest 40 centimeters above a positively charged pith ball B in a graduated cylinder as shown in the diagram. The mass of the bottom ball is 0.1 grams. Both balls have the same charge and mass. So let's list what we have. We know that the charge on A is equal to the charge on B. The reason I say so is because they say both balls have the same charge. So since they have the same charge, we might as well go and say that both of these charges are equal to Q, where Q is just a variable that we're using in the place of the charge because we don't know what the charge is. They tell us that ball A is held at rest. If we have an object at rest, we know based on Newton's laws that the net force on that object is 0 newtons, so 0. We know that both of the balls are positively charged, and we know that they both have the same mass. The mass is 0.1 grams, which means the same as 0.1 times 10 to the negative 3 kilograms, or you can simply divide by 1,000. But it's very important that you convert to the correct SI unit. Lastly, we also know the distance between the two spheres, or the two balls in this case. R is going to equal to 40 centimeters, which we can convert to meters as 40 times 10 to the negative 2 meters, or you can divide by 100. This is the information that we have available to us. So now that we've analyzed what we have, we can go on to question number 1. Question number 1 says, draw a free body diagram showing all the forces on ball A. Ball A is the one that is held at rest 40 centimeters above B. Ball A is an object which has mass. If it has mass, it means that there is a force, a gravitational force, that the Earth is exerting on that object. So this Fg is the force of the Earth on ball A, based on the fact that ball A has a mass. Now ball B is a charged object, and therefore we know that ball B is exerting a force on ball A. Since both of these objects have a positive charge, we know that we have like charges and like charges repel. So that means ball B is going to push ball A away. And we therefore can include on this free body diagram that there's an electrostatic force. We can call it the force of B on A if you'd like, or just the electrostatic force. And these are the two forces that are acting on ball A. Now question number 2 says calculate the charge on each ball. We know that the charges are exactly the same. And since we have the distance between the charges, we might want to use Coulomb's law. Coulomb's law says Fe, the electrostatic force, is equal to K Q1 Q2 divided by R squared. We have the proportionality constant. We also have the distance between the two balls. But we don't have the charges because that is what we're looking for. And we also do not know the electrostatic force. So we're going to have to come up with a plan to calculate this electrostatic force. The fact that they provided us with the mass of the two objects and told us that the objects are at rest is not by coincidence, it's not just for just. They've done it because we can use this information to calculate Fe. We know that the object is at rest, which means the net force is 0. And since we only have two forces acting on ball A, we know that the electrostatic force is going to be equal but opposite in direction to the gravitational force. So we can calculate Fe by saying the net force is equal to 0. Therefore, Fe is equal to the gravitational force. We know that Fg, the force of the Earth on the object, is equal to mg. M is 0.1 times 10 to the negative 3 kilograms. G is 9,8. When we plug this into our calculators, we end up with an answer given as 9,8 times 10 to the negative 4 newtons. This is the electrostatic force. So now remember, we want to calculate the charges. Since we now have the electrostatic force, we can use Coulomb's law. We can use this equation. And we can say Fe is equal to K Q1 Q2 divided by R squared. The electrostatic force we just calculated, it is 9,8 times 10 to the negative 4. K is the proportionality constant that we always have in our table of constants. As mentioned previously, Q1 and Q2 are the same, so we can simply say Q in the place of Q1 and Q in the place of Q2, or in the place rather of charge A and charge B. So if you would like, instead of using 1 and 2 in the formula, you can use A and B. That's also fine. We're going to divide all of this by the distance between them squared. The distance we converted, and we got 40 times 10 to the negative 2. We must not forget to square it, please, and we put the square on there. Now we can simplify this equation. Before we solve for Q, we can simplify it. If x times x is x squared, then Q times Q is Q squared, and we end up with exactly the same formula, but with Q squared. And now you can see we only have one unknown, which allows us to solve for Q. We manipulate the equation by firstly multiplying up by what's at the bottom. Then once we are done multiplying up, we divide by this. And since we want Q on its own, we take the square root. And then we are able to find Q. In the end, the value that we obtain for Q is that Q, which is the charge on QA and is the charge on QB, is going to equal to 1,32 times 10 to the negative 7 Coulomb. This is the final answer to this question, and that means that we are done with this example.